How are we doing today? AP Statistics. This is Chapter 5, Basic Data Transformations and the Normal Model. First, we're going to talk about some basic transformations we can make to our data and how those changes affect the center and spread. All right, so we're going to start by adding a constant. Of course, subtracting a constant is just adding the opposite. So when I say adding a constant, you could be adding or subtracting a constant to an entire set of data. That's what we'll be talking about first. So we're going to consider the graphs below, which depict the weights in kilograms of a sample of men, that's on the left, and the kilograms above recommended weight on the right. So there's a recommended weight, and the graph on the right talks about the pounds that you are above that recommended weight. And some folks are below recommended weight. That's why we have some negative values down here. So you'll notice that to get from the raw weights, that's the left, to the weights above recommended weight, 74 is subtracted from each data value. How am I getting that? Well, here we have 50. Here we have negative 24. Here we have 100, here we have 26. So there's a clear difference. We subtract 24 from each data value. So how does that affect the center and spread? Well, because of this, measures of center decrease by 74. We add a negative 74 to get from this graph to that, this set of data to that. Well, that means that the measure of center will decrease by that same amount. But will the spread change? Well, no. The measure of spread remains constant. If you're subtracting or adding the same value to each data value, then the measure of spread is going to remain constant. So in general, if you add or subtract a constant to all data values, that adjusts the center by that constant, but has no effect on the spread whatsoever. Now we're going to talk about rescaling data, all right? Now, if we adjust the scale on the horizontal or the vertical axis, we'll be adjusting the scale on the horizontal axis. That is an act of multiplication, all right? Multiplication or division, but what is division but multiplying by the reciprocal, all right? So multiplying data by a constant, rescaling, they are the same thing. So note that both data sets feature the same weights as before, except the graph on the right is the same graph converted into pounds, okay? So we take this graph over here and make a new graph, which is the same as this, except the units are different. The units are pounds, right? Refers to the same data set, but the units are different. We have rescaled. All right, and to rescale, you need to multiply by a scale factor. So if we know 1 kilogram is approximately equal to 2.2 pounds, that's not a perfect scale factor, but it's close. How will the mean change when kilograms are converted into pounds? Think about that. And also think about how will the standard deviation change when kilograms are converted to pounds. So how will a measure of center and a measure of spread change? Think about this for a moment, pause the video, and then unpause the video when you want to know the answer. All right, I'll assume we're ready to go on. So we have a chart here that shows how the minimum, Q1, median, Q3, max. So these measures of position right here, including a measure of center, the median, as well as some measures of spread, interquartile range, and standard deviation. So we have a measure of center and we have a measure of spread, all right? So how do those change? Well, when data are rescaled by multiplying by some constant, all measures of center, mean, median, position, min, max, quartiles, percentiles, what have you, and spread, interquartile range, and standard deviation, are also in turn multiplied by that same constant. And we can see this in the table to the right. So let's look at the median. That's our measure of spread. The mean is going to work the same way. Just trust me on that. But we have the median in our data table. Let's check this out. So we have 76.85 kilograms, and we multiply by 2.2. That converts to 169.07 pounds. All right, this is an approximation of that scale factor of 2.2, so it's not a perfect multiply by 2.2, and there you have it. But there you go. It's approximately 2.2. So that is the effect on the center and also other measures of position. What's different, though, this time is that the spread is affected as well. Interquartile range and standard deviation are measures of spread. That is a perfect multiplication by 2.2. That is a just about perfect multiplication by 2.2. All right. So we are changing everything here. So both center and spread change when multiplying by a constant. When you rescale, not only do the measures of center change like before, but the measures of spread also change. But only center changes when adding a constant. So multiplying changes center and spread. Adding a constant to all your data values just changes the center. The spread is unaffected. So now we're going to talk about the standard deviation, which generally in statistics acts as a kind of ruler or benchmark. So suppose a student were to earn a 90% in their math course and a 95% in their history course, right? So decent, good grades all around, commendable even. Suppose that the mean grade in the math course was an 85% and the mean score in the history course was a 90%. So both scores are 5% above the mean, but does that mean that the student performed equally well in both courses? What other information would be helpful in determining which academic feat was greater? Well, we need a measure of spread to answer that question that takes into account all of the data values. In statistics, we call that the standard deviation. The standard deviation is a measure of spread that takes into account all data values, okay? So that is going to be our determining factor for which class we did better in, the math course or the history course, right? So standardizing data values with z-scores. We have this equation right here, one of the most important equations we're going to talk about in all of statistics, but definitely in this section. Here we go. To standardize a value, that is to state its location relative to the mean and standard deviation, we subtract the mean from the value and then divide the difference by the standard deviation. What that means is x is our data value, we subtract the mean, and then we divide by the standard deviation. That process, take a value, subtract the mean, divide by the standard deviation, is called standardizing. So x is a data value, x bar is the mean of the sample, s is the standard deviation, and we will call z the standard score, all right? But we often call z just the z-score. Standard score, z-score, same thing. The z-score tells us the number of standard deviations a data value is above or below the mean. So for example, a z-score of 0.9, that's going to indicate that a data value is 0.9 standard deviations above the mean. A z-score of negative 1.2 indicates a data value is 1.2 standard deviations below the mean, right? So we're going to find a z-score for a student's test grade of 90 given a mean of 85 and a standard deviation of 10. Then we're going to interpret that z-score. So we just take these values, throw them into the formula. This is x, this is x bar, and this is s. Throw it in, and we get 0.5. So a score of 90 is 0.5 standard deviations above the mean. All right, now we need to talk about some effects of standardizing the data, okay? Though standardizing into z-scores does not change the shape of the data, okay? It alters the center and spread in really convenient ways, okay? Notice what we're doing. We are taking data values and subtracting the mean from each of them. That is adding a constant, all right, or subtracting a constant. We talked about what happens there. The center changes, the spread does not. Then we divide by a constant. We divide all of these differences that involve the data value by a constant. Dividing is multiplying by the reciprocal. So we are rescaling. We are multiplying by a constant. So that's going to change the center and the spread. So standardizing changes the center and the spread. All right, so we'll see how that makes things really convenient for us in statistics. Okay, analyzing the formula for standard score shows us that after standardizing, the mean z-score is 0. All right, so after we standardize, the mean z-score is always 0. Well, why? Well, the data value equal to the mean would produce a z-score of 0. Think about it. If I had the mean here, and I were to insert for a data value the mean, all right? Mean minus mean over standard deviation, well, that's going to be 0, okay? Standard deviation is some positive number, okay? So that's just going to be 0, okay? So that means that the mean z-score is going to be 0. If you substituted the mean for x, you would get 0. The standard deviation of the z-scores is 1. This is a little more sneaky, all right? Follow me. This is because the sample normally has a standard deviation of s, all right? So we have our sample. The average distance to the mean is going to be s, all right? But we take that spread of s in our initial set of data, and we divide each data value by s to get the z-score. So dividing all of the data values by s changes the spread from s to 1, okay? That's what happens when we rescale data. Remember when we converted from kilograms to pounds, we had to multiply the center and the spread by 2.2. So if we were to divide by s or multiply by 1 over s, we change our spread from s to 1. That's really cool. So now we have a mean of 0 and a standard deviation of 1. Those are nice, easy, workable numbers. We like that in statistics. All right, let's solve a problem using standardization. Many colleges and universities require applicants to submit scores on standardized tests such as the SAT, the verbal section, and math tests. The college your little sister wants to apply to says that while there is no minimum score required, the middle 50% of its students have a combined SAT between 1100 and 1350. Those are that's the middle 50% of the scores between Q1 and Q3 are in that interval. You feel confident if you knew her score was in the college's top 25%. But unfortunately, she took the ACT, which is an alternative standardized test, right? So, question is, how high does the ACT need to be to make it into the top quarter of equivalent SAT scores? So we know some facts about the SAT. Here's where the middle 50% would be for this college. Here is the mean SAT score. Here's the standard deviation of SAT scores. So since we know some facts about the SAT and also where the mean and standard deviation of the ACT are, we can use standardization to come up with an equivalent score for this guy, all right? This is going to mark Q3, all right? It's the upper end of the middle 50%. That would be the cutoff for the top 25%. You got 50% in the middle, 25% up top, 25% in the bottom, all right? So this is the cutoff for the top 25%. What is the equivalent ACT score for 1350, okay? So first thing we need to do is find the z-score for Q3. 1350 is Q3 for our SATs. What's the z-score for that? We're going to need to use this information as well to find the z-score. After we know that, we're going to find the ACT score that is Z standard deviations above the mean ACT score, and that's going to be our score for the ACT that corresponds with that top 25%, the lower cutoff for the top 25% that we want to be in. Okay, so feel free to pause the video and try this one on your own, or if you want to watch me do this problem, go ahead. Just keep going on with the video. All right, I'll assume we're ready to continue. Let's tackle this problem. First part, we're going to find the Z-score. That Q3 1350 goes right here. We have the 1083 is the mean SAT score, and the 191 is the standard deviation of the SAT scores. And we have this guy right here. I rounded to 4 places. Generally in statistics, you round to 4 places, you are going to be A-OK. Or if you're using percents, you can round to 4 places would be 2 places to the right of the decimal if you are using percents, but that is neither here nor there. Okay, so here is our Z-score. To get into that top 25%, we need to be 1.3979 approximately standard deviations above the mean. So now that I know the Z-score, I can take this information about the ACT and find the corresponding score that would get me this high above the mean. And that is what I shall do, okay? So 1.3979 times 4.8, that's my standard deviation. I want that many standard deviations plus 20.8 is going to be 27.5, all right? Now, if you know about the ACT, there's no such thing as a half of a point on the final scoring of the SAT, so you would want a score of 28 or higher, and that would place you into the top quarter of scores. So the score corresponding with a 1350 on the SAT is a 28 on the ACT, assuming all of this information is true and accurate.